Hi everyone, welcome to our video on the rules for derivatives and their graphs. So a smooth continuous function like a polynomial is differentiable everywhere. However, some functions are not differentiable at certain points. And it comes down to these three bullets. So a function f is not differentiable at a if at least one of the following conditions holds. So if f is not continuous at a, if f has a corner, or a wedge or a cusp are other ways to say it or to see it. So I would say sharp corner, really. A sharp corner might be a little better at A, then it would not be differentiable. And then F also, if F has a vertical tangent at A, it would not be differentiable. Okay, so for instance, what's really nice about these is that they're quick. So in this example, it says, given the graph of y equals f of x, so our graph is already shown, find the x values where the function does not have a derivative, so no derivative. So it's where we have one of these three happening. Okay, so beginning at 5, so we'll continue going here, where it looks like at our endpoint, or not our endpoint, sorry, at our corner right here is where we would not have a derivative. Okay, so leave a little space. I'm going to say something also about this negative 5 in just a second, but let's go for the clear one. So at x equals, this is at negative 2. So at x equals negative 2, it's not, no derivative, because it's got a corner, sharp corner. I'm going to write it as sharp corner. Okay, and then afterwards, well, continuing through, so this is continuous, so that's fine. So from negative 5 to here, that's continuous. From here, everything's good, but we see there's a sharp corner at x equals 1. So x equals 1, there's also no derivative because of the sharp corner again. Okay, and then the last part, well, this is continuous, everything's fine until we get to x equals 3. And then we see that it's not continuous there. So at x equals 3, there's no derivative because it's not continuous at 3. Okay, so there's the gap. Okay, so that's the clear ones. Now, in these bullets, so this is assuming that you can see all the graph. This is a special case, actually. So at negative 5, notice you have the big solid dot. So that means the graph stops right here. Well, at endpoints, we would also have, let's go ahead and add that. So at endpoints, there's not going to be a derivative. Endpoints, no derivative. Okay, so that means really, so that's why I wanted to leave a little space. So at x equals negative 5, there's no derivative either, because that's where the function has an endpoint. And then at x equals positive 5, there's also no derivative, because again, that's an endpoint. Okay, and the reason that it doesn't have a derivative at the endpoints or the sharp corners, so all of these four are very similar. It's because when doing the definition of a derivative, so just to remind, so when we have functions, it's f prime of x, so this is the derivative, equals the limit as h goes to 0 of f of x plus h minus f of x over h. So limits depend on it being able to go from the left side and the right side. So that's why this star here is going to be important. While the limit on the left at negative 5, there is no graph. So that means the limit on the left would not exist. And so that means this derivative has a problem. Okay, so that it's not defined there. Okay, so that's why that does not have a derivative. And same deal, after 5, there's no function. So that means the limit from the right would not exist. So that means this derivative would not exist. Okay, so from the right, there's a problem. Okay, and then similar with these, well, from the left, so this, where this not continuous, from the left and from the right, the derivatives, the limits would be equaling something different. Okay, so that's why that one doesn't exist. And same deal, really, at the sharp corners, from the left and from the right, we would get different values for the limit. Okay, so the limit represents the slope. So we can kind of see this slope here is a positive slope. It's up and to the right. where after the corner points, it's a negative slope. So it's saying a positive slope changes to a negative slope. So that's why the derivative has a problem. It doesn't match. The left side does not equal the right side. Okay, anyway, so that's the explanation. Here are the quick reasons, though, to our problem. All right, so let's see one other that is similar to this, where we've got, given the graph of y equals f of x, we want to find the x values where the function does not have a derivative. Okay, this time around, so there's no solid dot there, so we're assuming it goes like that. So that means I don't have to worry about anything to the left. And then all I'm looking for is, well, right here I have a sharp corner. So this is also called a cusp. So it comes in, so it's not just two straight line segments like above. It's got a little curve to it. But either way, it's a sharp, I would say it's a sharp corner. Okay, so at x equals, it looks like 1, 2, 3 to the left. So at x equals negative 3, we have, let's just say no derivative at x equals negative 3 because sharp corner. Or you could say cusp. I'm gonna still say sharp corner. And I'm using BC as because. Okay, so that's that. And then looking for, continuing going right, I see, well, I've got a gap here. So that means it's not continuous there. So that means at x equals 0, I don't have a derivative because it's not continuous there. So that's that. Okay, and then moving on. Well, in this picture, so it is continuous after that. And there's no sharp corner, but this is our third case. So this is a vertical tangent. They usually have to put in the vertical tangent line within a dash. So here we do have a vertical tangent. And so there would not be a derivative there, let's say at x equals 2, because vertical tangent line. Well, so if we were to think about the slope, so if you have a vertical line, so this is the reason why vertical line has an undefined slope. M is undefined. And since M, the slope of the tangent line, and the derivative are directly connected, if the slope is undefined, that means the derivative would also be undefined there. Okay, so that's that. So very quick problems, right? And then on the right, I'm assuming there's no solid dot, so it does keep going to the right, and I'm assuming we don't have an issue anymore. Okay, so there's the quick ones. Now, to make it a little more challenging, let's look on what else we have with these graphs of the derivatives. So the function f prime is called the derivative of f because it is derived from f. Now let us see how to derive the graph of f prime from the graph of f. So on most problems, we have functions where we can derive the derivative. But if we have the graph of f, we can still derive the derivative graph by using our picture. Okay, and what it comes down to is, again, a couple of bullets where it says for f increasing, we would have f prime is positive. So the slope of the tangent is positive, which also means the graph of f prime is above the x-axis. Okay, so what, and we'll kind of break those down. Let me just go ahead and make like a sketch here where I have a parabola. I think this would be the easiest way to look at it. Okay, so where f is increasing, so remember increasing means to draw it up from left to right. So I'm going to do that in red. So beginning at the vertex here, I would be drawing it up from left to right, right here. So this in the red is where f is increasing because I'm drawing it up from left to right, which means the slope is positive. Okay, and the slope is positive because, well, if I were to take, let me do it in one other color. Let's do it in green. If I were to choose any point, and you could choose any point in this red region, if I were to choose a point, and if I were to think, hey, what's the tangent line through that point? Well, I would have to draw it upward like that. So that's true anywhere I choose a point on the red line. You could choose, let me do one more here. It's still going upward from left to right. So that means the slope is positive. So going up from left to right as a slope, our slope is positive. Okay, so if f is increasing, that's why our f prime is positive. The other way that they might say that is f prime is greater than 0. So positive numbers are greater than 0. Okay, which means one other thing, when we start to graph just f prime, we know it should stay above the x-axis. Okay, so we'll use that information real soon. Okay, and then our second portion for f decreasing, so in my parabola that I just drew randomly, that would be this bolded blue section. So that's where I'm drawing it down from left to right. So that's where f is decreasing. So it's going down from left to right, which means the derivative, again, I could do what I did with like the green, choose a point, and if I were to think about the slope of the tangent, I'd have to draw it downward. And well, if I go down from left to right, that means the slope is negative. Okay, so that means our f prime would also be less than 0, which again means when we start to graph on its own, it would be below the x-axis. Okay, and then one major thing, is when f changes from increasing to decreasing or vice versa, so decreasing to increasing, then our f prime is 0. Okay, the reason for that is, well, this is if it's smooth. Okay, so when f changes from increasing, let's add that, if smooth. Okay, so if no corner point occurs, so those rules still apply. So like on this, it did go from decreasing to increasing, but there was a cusp there, so we have an issue there. However, like on this problem with a nice parabola that's nice and smooth, when we have, let's use one other color. I'm going to do it in this bright pinkish. Oh, that red, I don't know. Let's do it in this light blue. Okay, so where it changes, so it changes from it goes decreasing here to increasing. Well, if it's smooth, it goes from negative values to positive values for our derivative. So f prime was less than 0, and then f prime is greater than 0. Well, to connect a negative number with a positive number, we must have 0. So this is telling us our mtan equals 0. So we would have a horizontal line at that point where it reaches its vertex there, which also means that f prime is 0. So this is telling us f prime is 0 at that moment. Okay, which means if we were to graph it on its own, graph the derivative on its own, it would have an x-intercept there. Okay, so anyway, so let's take this information and break it down into two. So we've got two the graphs are the same, but let's break them down and see what they want. Okay, so let's use the points in the following graph of y equals f of x to answer the following. So in number 1, at which points is f prime of x greater than 0? All right, so all I'm going to do my colors one more time here. I'm going to draw where it's increasing. So I'm assuming there's a little arrow there, but from left to right, going along this graph, this is where it's increasing in red. And then it goes to decreasing, but then on f and after, it's increasing again. Okay, so where it is red, so remember where f is increasing, so I'm using this information in the red, where f is increasing, f prime is greater than 0. And they just used a different notation here. Okay, so that means any points that are on these red parts is where it is greater than 0, but not at the peaks, okay, because that we have another thing of information on, which we'll take it on very soon. Okay, so for number 1, where is this greater than 0? Well, it's where the graph is increasing, so it's at that A, it's at the B, not C, because, well, it looks like, I know on my graph it looks like it is, but it isn't. That's a peak, so that's where like my light blue information was important. But I do have one other, it's at G. So A, B, and G are these big A, B, and G values where it does satisfy that inequality, which again is just focusing on where the graph increases from left to right. Okay, and then where it decreases is, I'm going to kind of bold it with a ziggy since the blue is a little tough to see on the black ink. Okay, so right here is where it's decreasing. Okay, so this, and you could write it in words too. So this is f is decreasing in the blue. All right, so that means that's where the derivative would be less than 0, okay, because it's going down from left to right. Okay, and we can see, well, the points D and E is where that happens. Okay, and then the C value and the F points is where we have that special case. Let me bold it in these light blue color. That's where the slope would be 0. So there's the mtan equals 0. And then right there is also where the mtan equals 0. So it's at our C, and it's at the F. Another way to think of this is at C and F, we also know that f prime of x is 0. Okay, so where the slope is 0 matches the derivative also being 0. Okay, so we're going to take this information and use it to help us sketch a graph of our derivative. Okay, so we're gonna sketch the graph of the derivative. Okay, well, the best way to start with this is start where you have your x-intercept. So we're going to start with the m tan equals 0 information. So plot where f prime of x equals 0. So that's where your peaks are. So I'm just going to do a dotted line. So again, this is f of x here. Let me mark it. This is f of x. What we're going to graph is f prime of x. Okay, so that means f prime of x equals 0 where these have their peaks. So that means I'm just going to go and plot that on the number line. Or on the x-axis number line. So and then the f, I'm going to do the same thing and get those points. Okay, and then now let me go ahead and use my colors again with the red. Okay, so this is saying wherever this graph is red, I need to be above the x-axis. So where my f of x increases is where my f prime of x, I'm going to write it in this phrasing, is above the x-axis. Okay, so that's all. So there's all sorts of ways to re-say it. So that's what we said in the bullet portion. We started using the symbols afterwards. So there's all sorts of ways to write the similar information. Okay, so where this graph here is increasing, which is in red, our derivative is above the x-axis. Okay, I know eventually I have to come to this point, so I have to be above the x-axis left of C. So everything in red, so that means I'm above the x-axis left of C. Let's put that in words. Above x, let's say f prime of x is above x-axis. It's left of that C value. Left of C, and then not anything where the blue is, but also right of f. And right of that capital F, so not our function f. Okay, so right of f. Okay, so above the x-axis, left of C, but eventually I need to come to this point. So here I am above the x-axis, and our answers can vary. All I'm doing is just making sure it's matching the rules. So that's above the x-axis. And then everything to the right of f is also above the x-axis. So maybe something like that. Okay, so this so far is our derivative. And I'll highlight it at the end, so I'll have multiple colors. Okay, so that's that portion. So I think plotting where it has the x-intercepts first is the best way. And then now we'll just break down this information. Okay, and then one other thing where f of x decreases. Okay, so I use the increasing information second, and then now I'm going to use the decreasing information last. So f of x decreases is telling you that f prime of x is below the x-axis. Okay, and so in our picture from above, where it was decreasing is between C and F. So that means I know my f prime of x is below x-axis between C and that capital F letter point. But I also know eventually it needs to come back to these points here. So anything below the x-axis that matches this is fine. So here's below the x-axis, and then eventually it has to come back up though. But it's still, all of this is below the x-axis still. But I know those intercepts are telling me I need to connect the dots somehow. Okay, so that's what this looks like. So this, and that's it. We did it. Okay, so it's just making sure we understand where f is increasing or decreasing. F prime is above or below the x-axis. Okay, so this is our f prime of x. I'm going to highlight it. So that's this portion right here. This is our graph. And the answers can vary, so it could look different, but that is it. Okay, so this is just showing we can graph f prime of x as well on our own graph by itself. So it is its own function still, so we can graph it. Okay, so that's it. So if you do have questions, please let me know. Otherwise, thanks for watching, and I will see you again next time.